Hello everyone, I'm Sachini Peoni Ekanayaka. I'm a PhD student at the Department of Electrical and Computing Engineering, University at Albany State University of New York. Our paper is on sequential datum-wise joint feature selection and classification in the presence of external classifier. Now let's get started. In many real-world applications, features are not freely available. For instance, in medical diagnosis, features come at a cost that is due to the acquisition process, and each example includes different features. Nonetheless, accurate classification is critical and time sensitive. Therefore, making accurate predictions using the most informative features is essential. In such a setting, feature selection and classification have received considerable attention. Standard classification methods consider all features to be available during training and testing. In contrast, offline feature selection methods, for example, lasso, select a subset of features during training and use them during testing. To accommodate prohibitively large feature spaces, streaming feature selection methods perform feature selection during training as features sequentially arrive one at a time. During testing, all examples are classified using a standard classification method using the same subset of features. Static instance-wise approaches perform datum-wise classification but access all features during testing for that purpose. In contrast, dynamic instance-wise feature selection methods adaptively select different features to classify each data instance during testing. A major drawback of the latter approach is inherently their classification mechanism. Labels are assigned based on the smallest expected misclassification cost defined. Such mechanism may work well for some examples, but not for all, leading to considerable performance degradation. To this end, we propose a method that decides between the use of a simple internal classifier and a more powerful external one. Specifically, we consider features are sequentially acquired during testing. We use the posterior probability to continue or terminate the feature acquisition process and also to assess how difficult it is to classify each example. The difficult to classify examples are forwarded to the external classifier while the rest are handled by the internal classifier. Now I'm going to describe our problem with specific parameters. We consider a feature vector as shown here with k number of features. Xk is the value of the kth feature to a label y. Ck denotes the cost of acquiring the kth feature. Objective is to jointly determine the subset of features, classifier to be used, and the label of each example. This is our optimization setup. We define random variable r to indicate the last feature acquired before assigning a label to the current example. We also define random variable dr to indicate the decision reached about the current example based on r features. Our goal is to minimize this optimization function with respect to r and dr. The first term represents the average cost of acquiring R features, while the second term captures the average cost of assigning labels using the internal classifier. The third term indicates the average cost of forwarding the example to an external classifier. We solve the optimization problem using the posterior probability and dynamic programming as shown here. Specifically, optimum feature acquisition strategy is derived in terms of the last stage and any intermediate stage as shown here. Finally, the optimum decision strategy dr star is given by this equation. The proposed STFA algorithm consists of a training and a testing phase. In training phase, the interval from 0 to 1 is appropriately quantized to generate all possible posterior probability vectors, and then stopping and continuing costs are numerically computed. In testing phase, features are sequentially acquired using the numerical solutions determined during training. If the stopping cost is greater than the continuing cost, the next feature is acquired and the posterior probability is updated. This continues until a subset of features is acquired or no more features are available. If decided to stop the feature acquisition, the current example is assigned a label by the internal or external classifier. To test the performance of the proposed algorithm, we use this dataset and also compared with these baselines mentioned here. We used accuracy and average number of features as the evaluation metrics. As external classifiers, we used SVM and decision tree. This table reports accuracy and average number of acquired features for the proposed approach in baselines. We observe that the proposed algorithm achieves a good balance between accuracy and average number of acquired features, forwarding difficult to classify examples to the external classifier. This is critical in real-world applications where acquisition of features is either prohibitive or the feature space is large. Next, this figure shows the distribution of the number of acquired features during testing for the Magic Telescope dataset using decision tree as the external classifier. We observe that most examples are classified using the internal classifier with very few features. We also notice that when more than half of the features have already been acquired, algorithm tends to forward the respective examples to the external classifier, suggesting that these are difficult to classify examples. In summary, we introduced and studied problem of sequential datum-wise joint feature selection and classification in the presence of external classifier. Further, effectiveness of proposed approach is validated on number of real-world datasets in compared with existing algorithms. In future, we plan to extend the proposed framework to accommodate multiple external classifiers and evaluate its performance on complex datasets with a large number of features. Thank you so much for listening to my presentation. If you have any questions, feel free to email me. Thank you.